All right. Hi, everyone. Thanks for tuning in for another ACE machine learning live stream session. We do these 3 to 5 times a week. And today I have here with me Mido, who is a PhD student at McGill University, and Mila, the Quebec AI Institute. He's broadly interested in artificial intelligence and machine learning. He is also a visiting researcher at Facebook AI. And specifically, he's interested in investigating multi-agent approaches for efficient, large-scale deep learning. So thank you once again, Mido, for being here as part of the reinforcement learning stream at ACE, and I'll pass the floor to you.
Okay, thanks for the introduction. So I'll just get started. So hi, my name is Mido. This is joint work with Josh Romoff, Nicolas Ballas, Joël Pinault, and Mike Rabat. And in this talk, I'll be discussing the efficiency of reinforcement learning algorithms. So current approaches in the literature often have this trade-off between computational efficiency and sample efficiency. So methods that are the most computationally efficient usually have to trade off sample efficiency and vice versa. And so the question we want to ask is there a way to kind of get the best of both worlds, have computationally efficient reinforcement learning algorithms without necessarily sacrificing on the sample efficiency? This work was published at NeurIPS 2019, and there's an archived link here at the bottom if you're interested as well. So current approaches to deep reinforcement learning typically have this sort of multi-simulator architecture. You have a learner that's trying to learn a policy by exercising it in many different simulators in parallel. So in reinforcement learning, we typically don't have the IID assumptions that are typically made in supervised learning settings. And so, for example, by exercising the policy in multiple different independent simulators in parallel, it helps decorrelate the observations and stabilize learning. Additionally, as well, obviously having multiple different simulators allows you to gather observations in parallel. And so it increases your sampling rate and reduces runtime. So now if you want to scale this further, typically what you do is you create multiple copies of these learners and simulators. These could be, for example, running on different GPUs, different machines, etc. And now, after each learner computes a gradient, they all synchronize their gradients with the other learners in your system. So this is one canonical approach. And this is, you can show that this is actually mathematically equivalent to just having a single learner learning with many simulators. The advantage for writing it this way, as mentioned, is now you can actually distribute your training across multiple GPUs, multiple devices, etc. And so this is sample efficient because the learner is always learning using or gathering observations using its most up-to-date policy. However, it's not necessarily computationally efficient because of the synchronization step. So you can imagine if there's variance in simulator stepping times across learners, one learner is going to end up having to idle and just wait for another learner to send its gradients. So this is really prone to those sorts of issues. One approach to get around this, if you're familiar, are A3C style methods. So here, again, we have multiple learners, but now rather than synchronizing their gradients with each other, they're writing them to this shared memory buffer, the shared model. So the agents periodically pull the parameters from the shared model, compute gradients, and asynchronously write these gradients back to the shared model. So as mentioned, this is computationally efficient because now you don't need to synchronize. You can just work independently and write your gradients whenever you're ready. However, this can actually hurt sample efficiency because now your gradients that you're writing back to the shared model could potentially correspond to a stale version of your policy. So you're not learning using the most recent information that you have. Another approach, and actually maybe it's worth mentioning that this approach can actually also become unstable if you have a lot of learners writing to a shared model because this staleness problem really becomes exacerbated. Another approach, if you're familiar with Impala, is to just decouple acting and learning altogether, and this has acquired a lot of attention recently. So here you have multiple simulators just running constantly, periodically pulling the parameters from the learner. The simulators take their observations and put them in an observation buffer, and then you have the learner running independently and periodically pulling observations from the observation buffer and using it to improve its policy. So again, this is computationally efficient because, as you can imagine, the learning and acting is completely decoupled, so everything is running independently, completely asynchronously. However, Here, it's worth noting actually a small subtlety is that the observations that the learner is using to update its policy potentially correspond to an older version of its policy. So you have to apply this sort of off-policy correction. And these kinds of off-policy corrections can potentially hurt sample efficiency. And so again, this is computationally efficient, not necessarily as sample efficient as we would like. And it begs the question again, is there a way to have computationally efficient methods without necessarily having to sacrifice on the sample efficiency? Throughout the rest of this talk, we'll refer to each one of these units as an actor learner. So the learner obviously being the learner at the top. And here we'll refer to the simulators as actors because they actually exercise the policy. So synchronous batch learning, let's start out with just a really simple description of what this actor learner update might look like. So here, the learner will first send its policy parameters to the actors. The actors or the simulators then step through their simulators in parallel and send back their observations to the learner. The learner will then use those observations to compute a gradient. And then what it's going to do is it's going to average or synchronize its gradients with all the other learners in the network, and then apply, obviously, an optimization step. So this is, for example, synchronous batch learning, or A2C, if you're familiar with that method, but distributed over multiple different learners. Now, as mentioned, the issue here is that this global synchronization results in idling time. You have learners waiting for other learners. This idling results in low hardware utilization, reduced frame rates, and just slows down training overall. Okay, and so the question is, can we do something more efficiently here? Rather than globally synchronizing our gradients with all the other actor learners, maybe we can explore a different approach. And the avenue that we're going to explore are gossip algorithms. So these algorithms come from the control systems literature. And consider a different problem for a setting. Consider iterative decentralized averaging. Okay, so you have a network of agents, each with a local value, x sub I. And these agents are connected over some peer-to-peer communication topology. Okay. And the goal is for the agents to agree on the average of their parameters, but by only communicating with their neighbors asynchronously. So one very simple algorithm to do this is to have each agent send its parameters to its neighbors, non-blocking, so it doesn't wait for the message to reach its neighbors. And then whenever it receives parameters from its neighbors, it directly averages them with its own parameters. And it just repeats this process. And under certain conditions, you can actually show that this simple asynchronous local averaging algorithm is guaranteed to converge to the true average of the network exponentially fast. Okay, and so the idea now is to replace this global synchronization of gradients with this asynchronous local message passing of model parameters. Okay, so we actually experimented with some of these ideas in a supervised learning setting. I won't go into some of the details, but here, for example, we trained a ResNet 50 on ImageNet using 256 GPUs over a 10 gigabit per second Ethernet network. So this is similar to what you would have, for example, in a cloud computing cluster. And without getting into too much of the details, we can show that we actually can train better models in less time. Okay, so now going back to the reinforcement learning setting, here we want to replace this global gradient synchronization with this asynchronous local message passing. And we'll refer to this as a gossip-based actor-learner architecture, because we have these actor learners that gossip with each other. So here, for example, we have a directed ring graph, and agents will, after every single step, will just send their parameters, updated model parameters, to their neighbors, and average whatever parameters they receive with their own model. Okay, totally asynchronously. And now what we're expecting, obviously, is that by replacing this global synchronization with this sort of local neighborhood averaging, that now we reduce idling time, improve hardware utilization, increase frame rates, and speed up training. Okay, and to test this out, we ran some experiments on Atari games. So here we have an NVIDIA V100 GPU, 48 Intel CPUs. And in this case, actually what we do is when we add more learners, we just stack them onto the same GPU. In reinforcement learning, the GPUs are relatively underutilized. And so this is maybe one approach to improving hardware utilization. And here we'll compare A2C, which does this global synchronization, with GALA A2C, which, as we mentioned, does this asynchronous local model averaging. OK, so let's look at this first figure here on the left. On the y-axis, we have the number of simulators. So we go from 64, 128 to 192. And on the x-axis, we have GPU utilization. In orange is A2C, and in blue is GALA A2C. So first, looking at A2C, as we increase the number of simulators, going from top to bottom, from bottom to top in the figure, the GPU utilization of A2C actually decreases. And as mentioned, this is because the synchronization overhead increases. So as you add more simulators, it becomes more expensive to synchronize them all after each iteration. And so this ends up decreasing the GPU utilization. For GALA A2C, on the other hand, when we add simulators, we're not synchronizing them. And so all this means is now our GPU is just working harder. And so it improves GPU utilization. So for example, with 192 simulators, A2C is getting around 5 or 6% GPU utilization, whereas with GALA A2C, we're at around 90%, just because we've stacked all of the learners to run asynchronously on a single GPU. Now looking at the second figure, again, this shows number of simulators on the y-axis and CPU utilization on the x-axis. So actually, in general, CPU utilization improves for both methods as we increase the number of simulators. But GALA A2C is better able to leverage the CPU resources. And this last figure here shows energy efficiency. So again, on the y-axis here, we have the number of simulators. And on the x-axis here, we have frames per kilojoule. So how many frames are we able to step through per unit of energy, essentially? This is actually 1,000 frames per kilojoule. But interestingly, it actually seems that by keeping the hardware resources better utilized, GALA A2C, shown in blue, is actually able to run more energy efficiently than just regular A2C. Okay. And the hope is that this will translate directly to frame rates. Okay, so let's look at the frame rates and their relationship to hardware utilization for a second. So this first figure here shows training with 64 simulators. The second figure shows training with 128 simulators. Third figure shows training with 192 simulators. On the y-axis, we have GPU utilization, and on the x-axis, we have the power draw from the GPU in watts. And what we do is we probe the GPU at different time instances to get these samples, and we plot these points directly as a scatter plot. And the bubble sizes actually directly correspond to frame rates. So as you can see, by increasing the number of simulators, the GPU utilization for GALA increases, but at roughly similar power draw. So this explains maybe why we're seeing this improvement in energy efficiency, because we're getting better utilization with roughly the same energy output, roughly. Interestingly, also, what we see is these bubble sizes grow as we increase the number of simulators, and that's what we were hoping to see, that as we improve the GPU utilization, our frame rates, the number of images or frames we can process per unit of time, actually increases. Okay, so maybe before going to the slide really quick, the question now we want to ask is, okay, this was actually what we expected. By replacing this global synchronization with asynchronous local message passing, we expected hardware utilization to improve. We expected to increase our frame rates and so on. The question now is, how does this affect the quality of the learned policies? Because now we're doing this sort of asynchronous local message passing. And it turns out this sort of asynchronous gossip procedure is actually a principled approach to doing multi-simulator training. So quickly, for example, let's first look at global synchronization. So if we were doing global synchronization, not asynchronous message passing, suppose all of the learners' policies start at this point pi k. Okay, and suppose we have 3 learners. These learners then all take local gradient steps, and they go to these gray points. And then, because they're doing global synchronization, they go to their average, which is this policy here, pi k plus 1. Okay, now all the learners are at this point. Again, they take local steps. They go to these gray points. They exactly synchronize. They go to this red point, and so on. Okay, so this is global synchronization. Now, if we swap this out with GALA, so asynchronous local gossip. Again, all the learners, we initialize them at the same point, so they all start at this policy pi k. They take local steps, and they go to these gray points. If they were to exactly synchronize, they would go to this red point, but they don't exactly synchronize. They do this asynchronous local message passing, and they go to these blue points, which lie in the neighborhood of this red point. Okay. Now, again, they all take local steps. They go to these new gray points. If they were to exactly synchronize, they would end up at this red point, but they don't. They do this asynchronous local gossip. They go to these blue points, and so on. And what we can actually show is that all of the agent's policies, represented by these blue points, are guaranteed to remain within an epsilon-ball of this average policy, pi bar. Okay, and the size of this ball is depends on your learning rate, the communication topology, and your message delays due to asynchronous gossip. Okay. And so as mentioned here, the epsilon-ball characterizes learning rate, communication topology, and an upper bound on the message delays. The learning rate is something you can directly control, but maybe not something that you want to change. The communication topology is something that you can directly control. So if you have a very sparse communication topology, the policies are going to drift further apart. So the size of this epsilon ball is going to grow. However, if you have a more densely connected or well-connected communication graph, the size of this epsilon ball is going to decrease, so the policies are going to remain closer to each other in weight space. And then also the upper bound on the message delays, if you have a lot of asynchrony, the policies are going to drift more. And if you have less asynchrony, the policies are going to drift less. And this is actually a hyperparameter. So you can specifically set an upper bound on the message delays. You can say, for example, if you don't receive a message from your neighbor in tau iterations, block and wait to receive a message. Okay, so we have kind of these three little knobs for tuning the size of this epsilon ball if we wanted to. In red here, we show the theoretical bound from the paper. And in blue is the actual distance of these local policies from the average that we measure in practice. And so this red bound is actually quite tight. Okay, so now let's look at game scores. So here, this is just one game so far. This is Beam Rider. On the y-axis, we have the reward. And on the x-axis here in this first figure are the number of environment steps. So there's a 1 times 10 to the 7 here. So these are not 3 steps. These are 30 million steps. Okay. We do 10 runs for each algorithm. These curves here are the average over 10 runs. And these shaded windows are 95% confidence intervals. In blue, we show GALA A2C. In orange, we show regular A2C with this global synchronization. In green is A3C, so this kind of asynchronous parameter server approach that we talked about. And in gray is Impala, this approach that just decouples acting and learning. And so interestingly, actually, as expected, we see, for example, the sample efficiency of A3C is lower than that of A2C because of the asynchrony and the staleness in the gradient updates. Okay. Interestingly, by contrast, the sample efficiency of GALA A2C does not degrade over regular A2C. And if anything, also the variance bars for GALA A2C seem lower, so the method actually seems a little bit more stable. And actually, I should mention, for GALA A2C, we did not tune any of the hyperparameters. We directly used the hyperparameters for A2C. Now when we look at game reward versus walk clock time in hours, the gap between GALA A2C and A2C increases. And again, this is because, as we saw, GALA A2C is better able to leverage the hardware resources. It's maybe also worth pointing out something interesting here. While A3C was less sample efficient than A2C, versus walk log time, it's actually more efficient. And again, maybe even though the sample efficiency degrades, the benefits in computational efficiency outweigh degradations in sample efficiency. And now when we plot game rewards versus energy, again, we see that we're able to get higher game rewards with less energy. And again, this is probably directly related to the fact that we saw we're able to go through more frames with less energy, about 3 slides back. And we see similar trends across all the different games we looked at as well, actually. Okay, so in short, maybe a little, I don't know how we are on time, but anyways. So in short, GALA A2C improves the computational efficiency of A2C while maintaining sample efficiency, and it's competitive with the state-of-the-art reinforcement learning algorithms. Some really interesting directions for future work, in my opinion, are combining GALA with other learning algorithms. So here we combine GALA with A2C. So the local learners are running A2C, but you could potentially imagine combining this with other methods, not necessarily policy gradient methods, maybe Q-learning methods, other approaches, and so on. Another thing worth mentioning is potentially it'd be interesting to leverage more efficient communication. And what I mean by that is in all of our experiments, we used a ring graph, a directed ring graph. However, you can imagine using different communication topologies or even learned communication. So agents try to learn which other agents they should communicate with at a given iteration. So kind of form of attention. And the reason I think this is actually interesting is because, so in all of our experiments, as mentioned, we used a directed ring graph. And what we noticed is these policies are slightly different, but they remain within an epsilon ball of one another. And that actually seems to slightly improve the sample efficiency, which was a really interesting observation. potentially due to decorrelating observations, generating more diverse samples, and so on. We're not really sure why the sample efficiency improved, but we have some hypotheses. However, what we notice is if the policies drift too much, if the size of this epsilon ball grows too large, then the sample efficiency starts degrading, because now these policies are no longer very informative of one another. So there's really kind of a sweet spot. And so one way, as mentioned, to directly control the size of this epsilon ball is with your communication topology. So exploring different communication topologies, or potentially having the agents try to learn or assign attention to other agents. So that could be a really interesting direction here. A third direction, which I'm also kind of excited about, is using GALA-based or gossip-based approaches to improve exploration. So now here we don't just have a single policy running across many simulators. We have a group of diverse policies that are pretty similar to each other but slightly different, and maybe this could lead to better exploration. Anyways, so yeah, that's it. Thank you. This is my email in case you have any questions. Here is a link to the archive paper, and the code is also available at Facebook Research/Gala on the GitHub. Thanks. Yeah.
All right. Thanks so much, Mido. So we do have quite some questions here. Okay. So yeah, like right now would be the Q&A section, and I would encourage people who are watching to ask questions in the chat, and I will relay them. So we have a first question. So it mentions that, so regarding gossip, right? Mm-hmm. The major difference is between you're waiting for all of the information or all of the, mm-hmm. let's say the nodes to finish, and then they, I guess, update the gradient together. Mm-hmm. But does that mean that within, I think the question is saying, like within the directed ring graph you were mentioning, mm-hmm. within those kind of nodes, if that's the right term, like would they still have to wait within themselves still to update?
Oh, I see. So the algorithm that we ran right now, each of the local agents is running A2C. So yes, this part is synchronous. So the agents, the learner sends its policy to simulators, waits to get things back, and then applies an update. So this is just running A2C. That part is synchronous. The benefit is, at least there we actually keep the sample efficiency of A2C, but we only have to synchronize our small local set of simulators rather than all of the simulators in the network. So it turns out it's not too much of an issue. But as mentioned, I think one of the really interesting directions is where we try not just doing this synchronously, but maybe seeing if this is another algorithm that maybe can. So here we ran on A2C, but you can imagine maybe if you're doing running in other environments where even this local synchronization cost grows too high, you can try replacing this rather than being A2C, being some other method.
I see. And just to follow up on that, so what does it mean for speed then? Let's say you're adjusting, you mentioned within the topology, like how, mm-hmm. I guess how granular it gets, if that's the right term. Like, mm-hmm. and you mentioned that's a balance between, let's say, the sample efficiency and whatnot. So that also matters for computational like optimization as well.
So by fine grain, do you mean kind of how many simulators we assign locally per node? Is that sort of what the question is? How do we?
Yeah.
Oh, yeah. So actually, that's also really interesting. As mentioned, it is going to be a bit of a trade-off. What we did in the paper, at least, which we didn't get to explore this very much, but if you just use regular canonical A2C, each agent has 16 simulators. So we just stuck to that. We kept here, each learner is assigned to 16 simulators. And then if we wanted to add more simulators, we just added more learners. But I think what you'd want to do is the number of simulators you assign to each learner, depending on what this local algorithm is, whether it's A2C or something else, you would want to assign a local number of simulators to each learner in order to optimize the kind of computational profile of that agent to make sure it's running efficiently. So for example, if I added a lot of simulators here, it wouldn't necessarily be running efficiently anymore. And if I add too few, then it's maybe also not necessarily the best thing. So it is a trade-off, and we didn't explore that part too much. We kind of just stayed with the standard algorithm, and then increased simulators by just adding more learners. Yeah, does that answer the question? Or
Yeah, I think so.
okay.
I'll let them see if they have any follow-ups there.
Okay.
So another question is specifically about A2C. So the critic is learning the advantage. So here is, so I guess gossip affects how the gradient is calculated, but however, the gradient is still, it's related to how the advantage is being learned. So is there any change to the way, let's say, the advantage is being calculated?
So that's a really interesting question. Because now it's kind of slightly off policy, right? You're using gradients calculated from slightly different policies, and it would make sense in some way to maybe change the way you're calculating this to account for these off policy, in some sense, gradients, right? We didn't do that though. So I think actually that could also be another really interesting direction, because if you do that, as mentioned, if the policies drift too much, we see this degradation in accuracy. Maybe one way to kind of use very sparse graphs with a lot of learners is if you, without degrading sample efficiency, is if we were to then apply these kind of local corrections of some sort. So not sure what that would look like, but we didn't do that. So right now we're communicating policy, the policy gradients, or actually we're not communicating the gradients, we're averaging model parameters across learners. Yeah.
Oh, gotcha. Nice. So, just to follow up on that, so the way you explained it, it's like there's possible ways to account for that. Let's say using like weights or something, but right now you're kind of taking it as is.
Yeah, exactly.
Just to sum it up.
Yeah,
okay.
We're really just averaging any models that we receive from our neighbors, even if they're delayed or so on. And I think it's right to think about if there's a way to, I don't know, improve that somehow.
Awesome, thanks. What is the minimal hardware needed to run this?
So one GPU and however a few CPUs. So here we used 48 CPUs. So here I should mention the simulators are running on CPUs and the learner is running on a GPU. Okay. And we're doing batched inference on the GPU as well in this case, which I think a lot of approaches are moving towards batched inference on the GPU. But yeah, so minimal hardware, you need a GPU and a few CPUs. The number of CPUs you have are going to limit the number of simulators you can put on them. But yeah, minimal hardware, one GPU, a few CPUs. But you can obviously extend this to many GPUs across many machines and so on.
Gotcha. Thanks, Willie, for asking that question. So as for the main difference between GALA and I guess A3C, could you quickly, I guess, go through that again?
Yes. So A3C, you can think of it as having a shared model in some memory buffer. And what the learners do is they periodically pull this model, compute a gradient, and then asynchronously write the gradients back to the shared model. Okay. So this is kind of what A3C does, and it does this asynchronously. So by the time I write this gradient back, the parameters are not necessarily these parameters that I pulled. These could have changed, if that part is clear. For GALA A2C, we don't have any kind of central memory storage system. Each learner just has its own parameters. And then what it does, it just averages its model with its neighbors asynchronously. Okay. And by doing that, we're still guaranteed to remain within this average model, even though this average model isn't really tracked anywhere. It's kind of just a theoretical property. So this average model, the average of all the learners' models, is not actually computed anywhere, but the learners all remain within an epsilon-ball of it.
Gotcha. Yeah, that makes sense. Thanks. So one part that was mentioned in the, I think it's the related work, but it's okay if you don't happen to have the paper here. Hopefully I can describe it. Okay. So it mentions that there was some work that disentangles the data collection part from the network updating. So I guess the network updating being the learners. So the main difference between that and this work, like, could you, I guess, quickly describe that?
Yeah. So here the simulators are not affiliated. Well, So here the simulators are all running independently of the learners, and they're always just constantly running. And I think newer versions of these now have actually switched to doing batched inference on the learner as well. But at the time of making these slides, these simulators were actually doing inference locally on the CPU. But as mentioned, the evolution of these methods since I've made these slides now, they do batched inference on the GPU because it ends up being more efficient. Okay, but as of right now, they do inference locally on the CPU and just run environment steps. They pretty much just keep generating observations and putting them in a buffer. And periodically, they pull the new parameters from the learner. So this process is not synchronous. As we mentioned, at least GALA A2C, this part between learner and simulator was synchronous. So learner sends parameters to simulators, simulators generate observations, send them back to learner. And then the learners, and then we have multiple learners, and they average their model parameters together asynchronously. Here, you can think of this as being like one single central server, for example. And you can, so here we have one learner, for example, one central server. And all these simulators, you can think of each one as maybe like a CPU, for example. And the CPU is doing inference and generating observations and putting them in a buffer. So it's not communicating directly back to the learner. And now the learner has to take these observations, it's like a data set of some sort, and use them to compute updates. So you can see why this approach is attractive, because it kind of decouples GPU learning from CPU acting, and you're kind of learning as if you have a data set of some sort. But you have to be careful here. So what they apply is some kind of off-policy correction here, because these observations are not generated using the learner's policy, but potentially a much older version of it. What we described, at least so far, this learner has a synchronous process with the simulators, and it's always learning on policy. So that's why the sample efficiency kind of remains the same of the base algorithm. So the sample efficiency of GALA A2C, at least in our experiments so far, look to maintain the sample efficiency of regular A2C. So look to maintain the sample efficiency of an on-policy learning algorithm, whereas still getting the kind of computational benefits of asynchronous learning. Here, you are definitely getting great computational benefits of asynchronous learning, but it's off-policy learning, strictly, in that these observations do not correspond to the policy that's being updated. But I think another interesting direction, for example, is if these local A2C learners that we had were instead maybe versioned somewhat like this. Again, it depends on what environment it is you're running on. For example, if you're running in an environment where there's more variance in simulator stepping times and so on, because Atari is relatively cheap compared to some of the more expensive environments that exist now. But yeah, one interesting direction, for example, is to replace A2C, these local A2C agents, with these kind of decoupled acting and learning methods, and then have those learners asynchronously gossip with each other. But yeah, anyways. So
okay, nice. Yeah, I think that's a really good explanation. So actually, just to add on to that, so the off-policy correction happens, because the learner is taking the information from the buffer, which serves as a kind of the data set that's generated from actors. I'm kind of just like summarizing it basically. So because that data is the actor's data is treated as off-policy here, right? It is stored in the buffer. So the learner will, I guess, like when taking the data, like it will take the observations and apply off-policy corrections. Exactly. Yeah. So this, I guess in this case, so is this for this slide? Are you specifically talking about Impala only?
For this slide, I am specifically talking about Impala, but I think there are a lot of there have been a lot of similar methods since that do something very similar. So as mentioned. There's another method very similar to Impala, I think from the same authors, or at least an overlapping intersection of authors, where now rather than doing inference on the CPU, they do batched inference on the GPU, which is kind of what A2C does. But it still has this kind of decoupled acting and learning. So I think this is specifically talking about Impala, but this general framework has been built on and used quite a lot recently, at least.
Okay, gotcha. Yeah, because personally, I wasn't so familiar with the details of Impala. So, the way that the off-policy correction could be applied, I guess not only in Impala, but like in general, like it could be stuff like weighting, or it could be like depending on what policy it comes from. Like, are there other kind of off-policy corrections that you would mention?
So the one in Impala, and I think this is a pretty common approach, is importance. They use like importance weights, what you mentioned. So essentially, they weight samples by kind of how similar they are to the current policy, and then use those to do the updates. There may be other approaches, but maybe not as familiar with those.
Okay, gotcha. All good. Yeah, it's because like that's the one that kind of came to mind, but I felt like maybe there's something that like that I didn't specifically know. So I think there's another question from the same person who asked the hardware. What's a good balance of CPU versus GPUs? Like maybe I forget if you have covered all the details, but they wanted to follow up on this.
Oh yeah, no. So I haven't talked about that. A good balance of CPU versus GPU. I think it really depends on your application. So it depends on how expensive, first off, how big your model is, how expensive it is, to compute gradients. That relates to how kind of the size of the model you're trying to learn. So one is the size of your model is an important consideration, and the second is the environment you're trying to learn in. So how expensive is it to gather observations? And that's what's going to determine kind of the trade-off. For example, if you have a small model, but it's really cheap or really fast to get observations, you need a lot more CPUs than you do GPUs. And this tends to be kind of just a general maybe pattern in reinforcement learning anyways, is that you need way more CPUs than you do GPUs. Of course, now maybe if you now try and do simulation on a GPU, that ratio could change. But I think the most common approach right now is typically you need a lot more CPUs than you do GPUs. If your model becomes very big and it becomes very expensive to take compute gradients, for example, then maybe you need more GPUs if you want to do learning on the GPU. And now also if it becomes really expensive to gather observations to do simulation, maybe you want to use more CPUs in order to have more simulators. So it's a lot of considerations, but I would say the two most important considerations are how big is your model, like how expensive is it to compute updates, and how expensive is it to gather observations from your simulators or your environment. And that's what's going to determine this ratio of maybe how many GPUs to CPUs you need. But typical approaches, you typically need a lot more CPUs for most methods right now than you do GPUs. If you want to do simulating on the CPU. So it should clarify that part.
All right, sounds good. Thanks. They said it makes sense. Good info. Thanks. Yeah. So actually, I think we have one more question, if not more. So regarding, I guess, because one of the advantages of A3C is that I guess each agent, like they can explore a bigger part of, let's say, the state action space in like faster, because they are. I guess that's one of the advantages. Like, can you comment on how that is similar or differing or not, like kind of orthogonal to what you're doing here?
Yeah, so as mentioned, I think these two approaches are just two slightly different approaches for doing something similar. You want to train with a lot of simulators while not necessarily being bogged down by synchronization costs. You can think of A3C as having kind of a centralized copy of a model, and then applying updates to and from that centralized copy of the model. So that's a perfectly valid approach. What we're doing instead is, rather than having a centralized copy of the model, training is completely decentralized. So all the learners are learning locally and then gossiping with other learners. And so this is equivalent in some sense, theoretically, to training a single model, but the learners' policies are slightly different and so on. So the dynamics are also going to be a little different. But yeah, so that's maybe the clearest way I could describe it. Shared centralized model, whereas our approach is maybe completely decentralized. you don't need a shared central memory anywhere.
Gotcha. So a question just to follow up on that is, let's say at the very end, and this might be more of an implementation question.
Sure.
Like, let's say in the very end, you want to like use this eventual learn policy to do something. Like, would you eventually have like a big sync over everything, like at the very end, or?
What do you mean sync? What do you mean by that?
Because you mentioned like several different policies, like slightly different from each other, right? But then in the end, would you kind of aggregate them into one in a sense?
Oh, I see. Yeah. So at least what we did in the paper, I think, not that long ago, but I should double check. I think we just took the policy corresponding to like one learner 0, whatever that was. But I think another reasonable approach is just to average all their policies at the end, because they do remain within this epsilon ball. So in general, if you were to train them independently and then average at the end, that would not make sense. But here, their kind of policies remain aligned during training. So just averaging them at the end completely makes sense. And I think that's a totally valid approach.
Yeah, I agree. I agree with that. Yeah, I guess it wouldn't drift too far away because of that then. All right. I think that's all the questions that we have. Thanks so much for the talk. Like, that was super fun and super interesting. Yeah, and as I mentioned, ACE does 3 to 5 sessions of these each week. So feel free to follow us and subscribe for updates, and have a great day, everyone. Bye.
Thanks for having me.